Here we have a stainless steel post with a solid cross-section, A, on the figure, that is surrounded by a brass tube, B. They both rest on a rigid surface on the bottom, so we can assume that surface to be a fixed support. And then they are connected on the top by a rigid cap, and a force of 5 kip is applied on top of the cap. We are given the dimensions of the height of this assembly is 8 inches. We have the dimensions of the brass tube, so we have an outside diameter of 6 inches, and then the thickness of the tube is 1/2 inch. However, we are not given the diameter of the steel post, and this is what we need to determine based on the fact that we are told that both the steel post and the brass tube are sharing the load equally, meaning that they are resisting the applied 5 kips in an equal manner. Since we have been told that both the steel post and the brass tube share the load equally, we can write the equation of equilibrium. We know the 5 kips will be equilibrated by the portion of the load taken by the brass and the portion of the load taken by the steel. And because we know those two loads are equal, it would be just 5/2 or 2.5 kips each. However, remember that the purpose of this example is to determine the diameter D in such a way that the load resisted by the steel post and the brass tube are equal to each other. So for that, what we are going to do is set an additional equation, which is the equation of compatibility. And we know that both elements of this assembly, the post and the tube, since they are joined by that rigid cap on the top, would have to shorten as a result of the load equally if they are going to be working together, and they are going to shorten an amount delta. So we can write the equation of compatibility saying that the shortening of the steel post is going to be the same as the shortening experienced by the brass tube. When we substitute the values of the deformation, axial deformation, remember is the load times the length divided by the axial rigidity, we can substitute for the corresponding values for the steel post, so the load carried by the steel post, the length of that post divided by the axial rigidity of the post. And on the other side of the equation, we have the same deformation that would be experienced by the brass tube, which is the load taken by the brass tube, the length divided by the elastic modulus of the brass and the cross-sectional area of that tube. Note that because the steel and the brass carry the same load, these two quantities are going to cancel out. Likewise, they are of the same length, these quantities are cancelled out. So now we can write the area of the steel post as a function of the elastic moduli of the brass and the steel and the cross-sectional area of the brass. Remember, we know everything here on the right side of this equation, and what we need to determine is the diameter. So diameter, if we find out the value of the area, we can find out the diameter. So writing the value of the area in terms of the diameter would be just the diameter of a circle is pi r squared, but if we put it in terms of the diameter, it would be pi d squared divided by 4. And substitute for the corresponding values of the elastic moduli and the cross-sectional area of the brass. And all we have here is an equation with one unknown, which is the diameter of the steel post. And we find that that diameter has to be 2.35 inches to ensure that the load carried by the steel post and the brass tube is the same.